Hi, and welcome to the case study where we look at predicting diabetes using a lot of healthcare information. So we have a lot of data sets here from the National Health and Nutrition Examination Survey, and what we're going to do, we're going to basically run through this data set, try some machine learning models, even a neural network, and assess the performance. And it's a very good case study exercise for practicing your machine learning. So let's get to it. So firstly, let's not start there. Let's just open your healthcare analytics diabetes data. That's the name of this project here, and I already have it open, so let's get started. So firstly, remember I said we have a lot of data to work with. Well, you can read all of this here if you want on your own time. I'm just going to quickly run through the data sets we have. We have a demographic data set. We have a lot of medical test results here, blood pressure, body measurements, that sort of stuff. We have some dietary data, and then we have the lab test, the blood test results. So we have a lot of different metrics here going forward that we can use in our data. So you can see there is quite a lot of information here. And then in the fifth data frame, we have a questionnaire data set about lifestyle type behavior, all of this stuff, family stuff, family history, smoking, a lot of different stuff going on there. Oh, and then 6, we actually have the medical data set as well. So forgot that. Actually, we didn't use that. That's why I forgot that. So I'll just remove this one from here. I thought I used it, but apparently I did not. But that's fine. All right. So firstly, let's begin our case study. So let's import all the modules we'll be using here. And now, as I said, we have a lot of data sets to work with. So let's just import all of these data sets here. And what we'll do, we'll drop some columns here. So if you wanted to see what the columns mean here, you can actually see a lot of them are listed here. They have, as I said, some very weird names here, like abbreviations. They don't actually describe what it is. So if you want to see what this is, you're going to have to go through all of these different data sets here. Links to these, I don't know if I told you, are like these links right here. Complete data dictionary can be found. This is what maps these column names here to these abstract looking column names here. And we all join basically on the SQ, I guess it's the sequence number or something for the patient. So we drop it for the other data frames here. When we merge all of them together right here using concat, we just merge them one at a time, df1 to df2, df1 to df3. And that's how we end up with this very long data set. You can see we have 1700 columns. That is crazy. Honestly, I don't usually work with data with so many features unless it's images. So we can take a look at what this data set actually looks like in the end. So I didn't mean to run this again, but we can take a look at this. This was just to describe. So you can see the ranges, max, means, the percentiles, counts, all of those things. But if you want to see what the data actually looks like, and you can see definitely, obviously with so much different columns, you know you're going to have missing data. It's just inevitable. And you can see we have a lot of missing data with the NAs there. So what we're going to do, we're going to rename some of the important columns that we want. So we have ID, gender, these things here. And then we're just going to filter out those columns here. And then what we're going to do, we're going to just drop the NAs from some of the axes here, from all of the axes actually. So we don't work with any NA data. And we're using something here called variance threshold. We don't use it in this block of code here, but we use it in the other blocks of code later on. And I'll explain that to you as well. So now we have this cleaned up data. So we went from this 1700 column data to this here. So we can pull out, you can definitely pull out any of the features you want. We were just following some different guidelines here, and these are the things that they actually believe would be helpful in predicting diabetes. So one of the things we have to look for to predict diabetes is this here, glycohemoglobin. Now glycohemoglobin is a test result that tells you whether a patient has diabetes or not. If it's 0 to 1, it's normal. If it's above 1, it's a high risk, and if it's above 2, you're a diabetes patient. So I think the last time I got checked, I was at 0.6, so I'm safe for now. So like I said, we use variance threshold here. I should not have imported it up here, so I'm going to take it off so it won't confuse anyone. So what variance threshold does, and we use it down here, is that it removes all the features that have low variance. If a feature has low variance, it drops it from the data frame. It's a very good tool to use. Like, principal component analysis looks at only the most important features that affect the main predicted target feature you're looking at. Well, variance threshold is sort of like that, but more primitive, in that it just deletes the columns of the features that don't have much variance, because you're not going to get much predictive power out of something. It's like saying, what if everyone was 25 years old in this data set? There's no point to having that, because then it's not going to add any predictive ability or power to your models. So what we do here, we just fill some of the NAs here, fill it with the median missing data, and then we fill it with fill file with family income, and then we fill this to 1, so we assume if the data is missing, the person breastfed the information. So that's what we do. All right, so now moving on, we just set the ranges here now for the glycohemoglobin as well, to indicate to just basically summarize it. So 0 means no diabetes. This range is different actually for the range I actually found online. It's a different scale, so excuse me for that. 6 and above and less than 6.4 is diabetes, and 6.5 and above is a diabetic patient. So you can see we've transformed this column here, these ranges, into this: diabetes, no diabetes, and then you're going to be the middle people who are just high risk for diabetes here. So that's how we do that. So we have a very nice data frame to work with right now. So moving on, we can just do quickly before we actually start creating our model. We should always do a correlation map just to see what you can figure out. So you can see right now, diabetes and glycohemoglobin obviously correlate because we just extracted that diabetic feature from that. But looking at this, you don't see that much of the correlations except for the sagittal abdominal fat, I believe, and having high, well, it directly relates to glycohemoglobin as well. That one you can see this one as well, arm circumference, which means that if the person is fat, they're going to have fat arms. That makes sense. Apparently they also do grip strength correlates to arm circumference, which makes sense. So you can see this data does make sense so far. It's pretty cool to go through these correlation plots to see what variables are directly related to each other or inversely related. Inverse relationships would be negative numbers here, and they would be represented in dark numbers if they were here, but none of them have that much strong inverse relationship right now. So let's stop here and move on into the next section where we start creating our model. So stay tuned for that. Hi, and welcome back to the second section of our case study, where we'll be predicting using machine learning models if a patient has diabetes or not based on this data that we have here. However, as we saw previously, the glycohemoglobin and the actual diabetes column that we extracted from this column here was highly correlated, obviously, because the diabetes column was basically built using the glycohemoglobin column. So what we'll do, we'll remove that here, because that is pretty much like putting the target variable in your training data set, which you don't want to do. You want to actually use these values here to predict diabetes, which diabetes will be our target variable here. So this is our data set that we'll be using from the vast number of data columns we had previously. So firstly, we'll do something that is a bit kind of dumb, but we'll try it regardless, is that we're going to use a linear regression model, because remember, this is a numeric value here. So we can actually use a regression model to predict an actual score for diabetes, and then maybe we can actually use that afterwards to basically determine if a patient has diabetes or not categorically. But for now, what we're going to do, we just create our separate training and test data sets here from our diabetes. We create our linear regression object, we fit the model, then we make the prediction, and then we score it here. But remember, this is a regression, not a classification. So the score is going to be basically a mean squared error to tell you how close it was to the actual value in the end. And we have the final scores here as well, the regression score. So it's not good, as you can see. 0.12 is pretty bad. And this is what our prediction table looks like. Remember, we're not predicting classes like diabetes, high risk diabetes, or no diabetes. We're predicting actual values of this here. So that's why, and remember, this was just 3 different values. This is a categorical variable, even though it's a digit, but it could work for this as well. However, this is kind of a naive, dumb way to do this, but we just tried it. What we're going to do now is actually use a classification model or algorithm, machine learning algorithm, to do this. And the one we're going to use is AdaBoost with decision trees. So I don't know if you remember AdaBoost from your machine learning theory, but what it does, it takes a number of weak linears using decision trees here, or we can specify whatever classifier we want as a base estimator here, where I'm pointing to. But we can use a number of these here, and we're using 100 right now at different linear rates and a set random state. We're just going to basically build a strong linear out of these weak linears here. So let's take a look at this. So now we're going to go through the basics of sklearn, where you import a model, you fit the training data with the training labels, then you get the predictions, then you just get, well, we don't need the parameters here, but we get it anyway. And we just get a score, and we predict the score. So let's see what that ends up being like. And we get a 0.7, 70%. That's not too bad. So we can stop there for now, but just want to say we can do better than this. 70% is, in most machine learning situations with data like this, you can do better than that, unless it's like a really hard problem. I haven't actually explored the data on my own properly to see if it's a very hard problem or not, but I assume we can get close to 90% accuracy using some better models. So in the next section, we take a look at how we can improve those classification models and then do a summary of those model results, just for some nice visualizations at the end. So let's stop there, and then we'll move on to the third section, where we start improving performance. Thank you. Alright, so welcome back to section 3, where we use some more models, more machine learning models, to try to get better performance out of our diabetes prediction. So let's go on to this. So what we're going to do now is use a bagging classifier. Bagging works similarly to boosting in a way, where we basically take a bunch of classifiers again, but instead of using weak linears, we use a bunch of decent classifiers. Well, that's trained using k-fold cross-validation at different samples of the data, and then we create what is called an ensemble classifier, which has like voting to get the actual final prediction. So they're usually quite good. Okay, so what we do, it's very easy to use these things on sklearn. We just import the bagging classifier here. We set the base estimator. We just set some of these default features here, and we just fit, predict, get the score, output the score, and we got 87%. And look how quickly it did that. Wow. So in a matter of like a split second, we just improved our machine learning model to 87% accuracy. That is quite good. Now let's try something else. Let's do the same bagging classifier, but instead of using a decision tree as a base estimator, we're going to do a key neighbors classifier here. So let's see if we can get better accuracy, and indeed we do. We get 88%. So wow, that's pretty good. So now let's actually try something called gradient boosting, of also famously known as XG boost. So let's call it XG boost here. And XG boost is basically a gradient boosting type classifier. You can look it up if you want. It's quite popular and famous. However, see, it's taking longer to train, maybe about a couple seconds longer, and it didn't get the same accuracy that the bagging classifier got on the test data set. Got 88% and got 87%. However, while these are all pretty good, can a neural network do better now? Because we can use the MLP classifier, that's multi-perceptron classifier, that's built into sklearn. It's not the best neural network framework library to use, but it does a job for small data sets like this. And what we're going to do, we're going to try and see whether we can use this to predict diabetes, to predict if a patient has diabetes, using our diabetes data set. So now let's run this on our training and test, sorry, on our training data here, and then to get the scores from our test data. And it does take some time, because it's a neural network. It has to go through many different iterations when we're doing this. So different epochs have to continue So we'll wait and see until it's complete, and maybe in about 30 seconds or so we'll get the results. Alright, so there we go. So we got the results. Let's see what we got. So 88% is quite good. However, look at this number. It's exactly the same as this number. So what does that tell you? Well, it tells me one thing. It tells me that our test data set, which we can quickly explore if you want to, just get the code. Sorry, that's right. It just came up. Our test data set looks like this. It has 3,813 rows, and it's telling me that if no classifier, even a neural network, could get better than this, that means there are some values here that either could be 1, mislabeled, or 2, completely throws off the general trends the machine learning algorithms have learned. Maybe it could be someone who's slim, who is male or female, who is young, whatever, not breastfed, and then probably gets it entirely wrong, because it's almost like an outlier. However, if you have a significant number of those outliers, which we do, which is roughly 12%, it means that we probably need to add some more features to this data set to get better accuracy. So this was more of like a teaching type case study to show you how you can actually use a lot of data, extract the relevant fields, or what we think are the relevant fields, and use it to predict diabetes. So what I would like for you guys to do is probably try some different features here from those data sets and see if you can get better than 88%. So now we can quickly just summarize the performance of models. We can put it into a data frame like this. Remember, we stored the score. I don't know if I didn't mention it to you guys directly, but we were storing the score for each model that we used. So we have it here, so we just quickly put it into a dictionary here, and then convert that dictionary into a data frame, and then we can have this little summary right here. So we can actually do this, and we can actually sort values by accuracy, and we can do ascending equal false to get the higher one on top, and it can give you this. Actually save our data frame like that, so that when we plot it, plot looks nice. So we can see, yeah, so it's a quick summary, and we can see MLP and bagging key neighbors tied for first. And then we can just do a quick little plot using the built-in plotting library within Pandas, which uses matplotlib, by the way. And we can get this little chart right here. So you can see, actually, it would look nicer if this was true, to be honest. I find it looks a little odd, having the larger columns on the left. Yeah, this looks a little bit more natural to me. So you can see you can actually plot all your classifiers that you've tried in models and get a final little output table if you wanted to present to your boss or your research supervisor or someone to show them a summary of your results, or even in your research paper you can do this. So that concludes this lesson. I hope you enjoyed it. I thought it was a pretty fun lesson personally, and actually I'm going to start playing with this data more, so maybe later on I might update this video with some more findings. So thanks for watching, and any questions, feel free to leave it for me on the Udemy forum. Thank you.
Subscribe now and press the bell icon. Never miss an update.